All right. So I'm just gonna get going so you guys catch up. All right. Yesterday we had homogeneous over on the left. We had heterogeneous on the right. We're gonna continue in our little columns here. Let's just get a few more examples. So if you're still putting books back, just try and catch up. All right. So homogeneous, we had salt water. What else did we have? Coffee. What else? That was it? Okay, let's put air. Air is homogeneous. It's uniform. Everything in this room, the air in this room is uniform no matter where you stand. You can't see anything. There's one phase. Okay? Someone give me a food. Could be a drink.
Tea.
Chocolate milk. Tea. Chocolate milk. Tea. Good. Heterogeneous. What do we have? Dirt, Italian salad dressing, is that it?
Ramen.
And ramen soup, right. Let's just add this, salt water and sand. That's just more of a, like, you might see that on a test. I don't think ramen soup is going to be on a Regents, but, all right. How do you separate heterogeneous? I don't know if we wrote this down yesterday. Can be filtered. Can be filtered. Oops, filtered. Homogeneous, you cannot filter it. Cannot filter because it'll go right through. I showed you that yesterday. Salt water went right through. So the only way to separate homogeneous would be distillation. Chromatography, I'm going to put over here. But technically you could use it here, but that's a little confusing, so I'm not going to really get into that. If you look at ink, right, if we took this red, black, and blue ink and we made marks on paper, it looks like one phase. So it looks like the blue is just one blue ink, one black ink, one red. So it looks and has a definition of homogeneous. So we're going to say homogeneous. Okay, chromatography we can use for that, and then it's starting to work already, but I'm going to show you something in a second. Besides distillation, we can be more specific. So distillation uses boiling point. So I'm going to also put freezing, melting, subliming, dissolving, ... There's other words there, phase changes, physical changes, but if you have a mixture of liquids, you can freeze them and then take the solid particles out as they freeze at different points. Same thing with melting, subliming, deposition's the opposite, boiling for distillation. So you could use their differences in melting, freezing, boiling points to separate. That's what I'm getting at, okay? This is the biggest way to separate homogeneous. The only other way you can do, or heterogeneous, is like physically pick things out. Okay, some sort of strainer or use forceps, right? But this is the big one. You cannot filter. You can filter, right? And that was the point of showing you yesterday. All right. Okay. Copy this down in your notes, this picture. And this isn't going to be in a museum anywhere, so don't take like 10 minutes copying this down. Okay, it's the image of distillation. I just want you to have it copied in your notes so you have a visual in there. Okay, so this is what a distillation setup looks like. Same one from the book, just looks a little bit different. So go ahead, copy that down. Make sure you write somewhere near it, this is distillation, so you know. You don't have to label it. You don't have to label anything. Just draw the picture. Okay? Just draw the picture. So in here would be tap water. Tap H2O. Over here would be pure or distilled H2O, right? All the sediment in the water would be down here at the bottom of the flask. It doesn't boil, right? So this is based on boiling points. Water has a lower boiling point than those solid particles. So the water evaporates. The cold water coming in here from, it's essentially tap water, is going around this tube. The inner tube here, the inside tube, has the hot vapor that condenses and then drips into this flask. So this cold water in and out never touches the vapor. There's glass in between them. It just cools it down. So that's distillation. Again, the definition is important to remember. Using boiling points to separate, because every substance has a different boiling point. So if you have a mixture of substances, you can separate them because they will boil at different points, different temperature. And it's not that easy. You need all the equipment and contraption and stuff, but if you ever get stranded on a desert island, you just got to get some ocean water in a hollowed out coconut shell, build a fire with your hands, put that over the fire, don't catch it on fire, but just heat it up, and then get a big leaf from your tropical trees, put it above it at an angle. The steam will hit the underside of the leaf, and put your mouth at the other side of that, and you will drink pure water. Or another coconut to catch it might make more sense. So remember that. But you got to start the fire first. That's not the easy part.
You did say with your hands.
Yeah, just rub your hands together really fast over some brush. I remember when I was a little kid, somebody told me to do that, and I was like amazed. I'm like, whoa, my hands are getting hot. Maybe that's why I like science. I don't know. It's cool to a little kid. They don't understand why their hands get hot. No, you'd have to whittle, you'd have to use some sticks, right? Anyways, enough of that weird analogy. But that's distillation. All right, so I'm going to move on. So that's distillation. And the next one I want to write down is chromatography. That's not it. There it is. Okay, do not copy this. I'm going to talk about it. Don't copy it. But in your notes, let's write chromatography. And it's a method to separate mixtures. And ink is the most common example. And the only thing I'm going to put is the ink must dissolve in the solvent. So what that means is this. I'm going to be standing in front of this, so I'll wait. So chromatography, method to separate mixtures. Ink is usually the one used as an example. But you could, whatever the substance is, it's almost always a liquid. You get some sort of paper or rigid surface here. You put the liquid on it, a couple spots there. Ink, again, is the example. The solvent, this here, usually water, will climb up the rigid surface. And if this ink dissolves in this solvent, so the water, as the water passes through it, it will separate into different components if it has different components. So this separated dye here, this dot, has two components, right? This one has the blue but doesn't have the yellow. Don't worry about that for now. The point here is that these two are different. This has two parts, that has one. But as the water flows up this paper, capillary action, so they will separate because it dissolves into solvent. So if I use this black ink here on the paper, as the water passes through, nothing would happen. Okay? You can see here, this is the black one. Can you guys see that? Different colors. There's like yellow, orange, red, blue. Multiple parts in the black. The blue one here, get in there. Oh no!
You messed it up.
No, everybody's okay.
Are you
So the
serious?
blue, it kind of looks purpley blue, right? So there's only kind of like one part. That the purplish is just kind of what the water does to it, as far as it's not really, it's separating into one part.
Looks like lined paper when you get it wet, like you spill water.
Yeah.
on it.
Yes, it does.
After it dries
It
up.
must
like,
be it dissolves in water. And then the red basically stays red. So the blue stays blue, basically. Red stays red. The black one is the one with different parts. So you could argue the black is heterogeneous, but you could also argue it's homogeneous because it looks like one substance. It looks like one thing, uniform, right? But that's what chromatography does. That's the simple reagents explanation. What do you need to know? How chromatography works. That's it. Water passes through, dissolves it, and you see the parts. That's the basic. AP Chem, College Chem, what we talk about is why is this blue dot here? Why is that yellow dot there? And the reason is forces of attraction. So the dye here is attracted to two things, the paper and the water. So as the water travels, this blue part, this part of the dye, is more attracted to the paper than the water, so it gets out of the water as fast as it can. The yellow one is more attracted to the water, so it stays with the water, hitches a ride a little bit further, then it finally comes out on the paper. So the higher the dot is, the more attracted to the solvent it is. The lower the dot, the more attracted to the paper it is. You do not need to know that, but I feel like I should explain everything you're looking at, okay? All right, and this is just, like I said, the solvent, so that means it's not part of, it's not a separate part, it's the same color, right? So it's not one of those parts. So anyways, that's chromatography. You should have done it in biology, is that true? You've talked about it, you've seen it, right? Mm-hmm. One more thing I want to show you here. Got a couple minutes. This contraption here. So this is a little out of order with the notes, but that's okay, we'll survive. Lights, please.
No.
Write this word down. Thank you. Electrolysis. Who's heard that word before? Nobody? Well, this is how we perform electrolysis. I'm going to fill this up with acid and water. I'm going to plug this up with two electrodes with wires connected to the black and the red here. And I'm going to hook it up to power on the lab table. Bless you. I'm going to run electricity through this. When you run electricity through water, it splits. This is how you split a compound. So we're talking about separating mixtures, which is physical. So while we're going backwards a little bit, we talked about compounds the other day. This is how you separate compounds. So let's write this down. Hold on a second. Is something going on with that? Okay. Electrolysis is using electricity. Using electricity to separate compounds. And that is a chemical process. So chemical. That's a chemical process. And the example would be water. If you take water, draw an arrow, put ELEC over the top, you run electricity through a sample of water, you will get hydrogen gas and oxygen gas. That is a chemical process. I'm bringing it up now because it's a separation technique, but it's for compounds. So I'm just making that clear. Filtration, chromatography, that's for mixtures, that's physical. This is for compounds, okay? This is cool. These fill up with hydrogen and oxygen gas, and then you open them up, and the gas comes out, and you light it on fire. That's cool.
Are we doing that today?
Well, no, because the bell's going to ring in a minute. But we are going to do it. Yeah.
Yay.
Question? Okay. You sure?